Hi, thanks for stopping by Team 16's booth. Together, my name is Zach McKinney. We've got Brandon Ward, Keith Snyder, and Eric Bentley. We've called our project the Smart Current Analysis and Data Acquisition Project. It's a bit of tongue-in-cheek reference, engineering humor. The SCADA industry is multi-billion dollar. We're on a shoestring budget. What we're doing, Smart Current Analysis, we're taking two signals. From the two phases coming into your house, the two wires going into your main breaker. We've got current transformers. Mine are a little bigger because I have big fat wires coming into my house. We're measuring that current signal. We're doing a fast Fourier transformer on this microcontroller. It's amazing. $19. It's about the size of your thumb. The particle photon. We're able to do a fast Fourier transform on it along with some other calculations and send all that data up into the cloud. That's the data acquisition part of our project. We're able to make some cool charts and graphs, build some dashboards, and look at that frequency domain analysis. It looks like my air conditioner is running right now. So with that information, you can tell what's on, what's off, and how much power everything's using. Maybe it'll motivate you to make it a little warmer in the house in the summer, a little cooler in the house in the winter, turn that thermostat down on your water heater. But what we found is there's this base load of power consumption going on in your house. Every phone charger that's plugged in, every LED light on every electronic device, every light in every kid's closet is on. So you can go around and turn off devices like that and reduce your base load without making it uncomfortable to live in your house. I live in Houston, Texas, so air conditioning is a necessity in the summer. Brandon's up in Illinois, so heating is a necessity in the winter. And we don't want to be cold in the winter and hot in the summer any more than we have to be. So this gives us a tool to reduce our power consumption without affecting our quality of life. The cool thing is once the data is in the cloud, you do these charts and graphs. You can consume the data with some web-hosted applications and make more charts and graphs. It's available on your phone if you want. And one of the things we're most proud of is if you look, there's a couple of web addresses. One's for our charts and graphs, and the other is for where we've shared this information freely on a DIY community website, hackster.io. Detailed instructions, step by step, what pieces of equipment you need to buy, and copy and paste code, so you don't even have to program anything. You just buy the equipment, put it together, and then start looking at those cool. Man, my air conditioner's still running. I have to turn that down. Anyway, I'm going to turn it over to Brandon. He's going to talk to us about the hardware side of the project, the smart current analysis part of the project. After that, Keith Snyder is going to talk to us about the Internet of Things architecture we've used, the data analysis, all the programming that went into it, the software, the dashboards. And then Eric Bentley is going to talk about our final deliverable. He's going to tie a nice bow on it, let us know about the budget, and give us some closing comments. So with that, thank you very much for stopping by again, and I'm going to turn it over to Brandon.
Thank you, Zach. Brandon here. I'm going to show everybody a little bit about our hardware and how we're collecting the data and analyzing it before we send it to the cloud. So the idea here is that we can take all of our loads that you see here in this panel, and we can analyze all the loads, or the majority of the loads, through these two CTs here from the main power coming in, and send that information to our photon and process the information there. So I'm going to show you what the sine wave of our currents look like. We've got our leg 1 and leg 2, and then I'm going to turn on the microwave and show you what that looks like. So you can see the first leg picked up quite a bit whenever I turn the microwave on. I'm going to show you what that looks like in an FFT. Right now I'm monitoring leg 1. I'm going to do an FFT on it. This is with about 5 amps on it. I'm going to go turn on my microwave and we'll show you what happens to the 120 harmonic. Okay, so you can see that the harmonic at 120 hertz picked up quite a bit. So that's one way of looking at this and saying that we can tell if something turns on. All right, this is the circuit all put together. This is something I put together that was more portable. And I can take it to family members' houses and try to identify appliances at other households. So found that a lot of washing machines, between myself and the team members, found that a lot of washing machines are somewhat similar. Microwaves are very easy to identify. Wells are a little bit more difficult. I practice a little bit. You really need to know a little bit more about the well pump, the mechanical makeup of the pump, how many vanes it has, and what the speed of the motor is. And then you're able to calculate. Or you can use an oscilloscope if you have access to one of those, and measure the do an FFT on your oscilloscope, which will make it a lot easier. So that pretty much does it for me. I'm going to turn it over to Keith, and he's going to go over the script he's got crawling through our spreadsheets every night.
All right, thanks, Brandon, for that look at the hardware. My name is Keith Snyder. I'm going to give you guys a quick look at the software side of our project. So you see what we have here on the screen is just a Google Sheets document, and it's receiving data from the particle photon that's in my garage attached to the main breaker panel. You see in the blue here we have phase A, and the red we have phase B. For each one we have RMS current and frequency magnitudes from 20 hertz to 200 hertz. If I scroll down to the bottom here, you can see it's getting a new sample about every 8 seconds. And we can take that information and look. You can see here, for example, the RMS current on phase B went up 5.5 amps. So what you could do is just copy these two rows and find the difference between them and put them on this page, which is our appliance signature. So this is each one of these appliances, how much the two rows change when that device turns on. So then we've written a script that at the end of each day archives all the data to a separate sheet. It then goes through that separate sheet for each one of these appliances. For example, here's yesterday's data, and it tallies up how much power was used by each appliance. So then once you have all that information here in Google Sheets, it's very easy to just make graphs. For example, here's the RMS current on each phase. If you want to look at the individual frequency magnitudes and how they change when things turn on, you can do that here. You can then make some graphs for, say, your daily power usage and a breakdown for each day by appliance, so you can tell which appliances are using the most power. Once you have these charts in Google Sheets, it's very easy then to go into Google Sites and just import your charts, so you have it here in a nice format that you can view on any device you like. That's all I've got for you. I'll send you now over to Eric to close us out. Thanks.
Thanks, Keith. When we first started looking into this project, cost was always a primary consideration. We figured that anyone looking to more closely monitor their energy consumption was going to inherently be more financially conscious. Our original budgetary goal was to remain under $100, but we were able to further reduce that figure to a final total of $59.16 just by simplifying the hardware used. This was pretty awesome considering off-the-shelf products that perform similar functions cost upwards of $300. So we're essentially offering a DIY home energy monitoring solution for less than 20% of the cost of market comparable solutions. For deliverables, we've uploaded the entire project to Hackster.io. This includes your shopping list, schematics, step-by-step setup guide, and code to copy and paste. So with about $60 and 3 hours of your time, you can follow the link at the center of our display board and begin to more closely monitor how much of load of laundry costs you to dry. So to sum everything up, it's safe to say that we've accomplished what every project team sets out to. We finished the project on time and under budget. I hope you have a chance to take a look at our deliverables on Hackster.io and maybe build a SCADA device for yourself. If you do, let us know how it worked out for you in the comments section on the project webpage. On behalf of Team 16, thank you for your time and attention. Enjoy the rest of your demo day.